Welcome to this video on redundancy and backup systems for reliability. Redundancy is one of the most important concepts in computer science and system design. In this series, we'll explore how redundancy helps systems stay operational even when components fail. Whether you're learning about data centers, networks, or critical infrastructure, understanding redundancy is essential. Let's dive in and discover how backup systems make technology more reliable. Redundancy is the practice of having duplicate or backup components in a system to maintain reliability. The first key aspect is fault tolerance. This means the system can continue operating even when individual components fail. The second aspect is data protection. By storing multiple copies of data in different locations, you ensure that even if one copy is lost or corrupted, you still have access to your information. Together, these principles form the foundation of robust and reliable systems. There are three main types of redundancy used in system design. Hardware redundancy involves duplicating physical components like servers or drives. Data redundancy means storing multiple copies of information across different systems. Network redundancy provides multiple connection paths so data can flow through alternative routes if one path fails. Each type serves a specific purpose, and often systems use a combination of all three to achieve maximum reliability. There are two main approaches to implementing redundancy. Active redundancy continuously monitors systems in real time, detecting failures immediately so that action can be taken before users notice any problems. Examples include real-time virus scanning or GPS error detection. Passive redundancy, on the other hand, only kicks in after a failure occurs. Think of it like extra strength built into bridge cables or extra tape on a package. The backup components aren't actively working until something goes wrong. Redundancy is critical in many real-world systems. In data centers, organizations use dual servers with data replication, multiple power supplies, and redundant network paths to ensure continuous service. In network systems, companies connect to multiple internet service providers, maintain redundant routers, and use load balancing to distribute traffic across multiple servers. These implementations prevent service interruptions and protect businesses from losing customers or critical data during outages. Implementing redundancy effectively requires following best practices. First, identify critical components using failure analysis to determine which parts are most important to your business. Second, choose the right redundancy model, whether that's active-active, active standby, or N+1, based on your specific requirements and budget. Third, implement failover mechanisms that automatically switch to redundant components when a failure is detected. These practices ensure your redundancy investment delivers real protection. Redundancy requires ongoing testing and maintenance to remain effective. Regular testing includes conducting periodic failover drills to ensure backup systems work when needed, performing system health checks to identify potential problems early, and validating that all components perform as expected. Monitoring and alerting systems must continuously observe system performance in real time, automatically notify administrators of issues, and track performance metrics. Without regular testing and monitoring, redundant systems can fail without anyone knowing until a real disaster occurs. While redundancy provides many benefits, it also comes with challenges. First, cost versus benefit. Redundancy significantly increases infrastructure costs, so organizations must carefully calculate whether the investment is worth the reduction in potential downtime losses. Second, complexity. Managing redundant systems requires expertise, continuous monitoring, and regular testing to keep all components synchronized. Third, geographic distribution. Spreading redundancy across multiple locations reduces risk, but increases network delays and makes data consistency more difficult. Finally, hidden single points of failure. Redundant systems may share common dependencies like shared power supplies or network connections, creating vulnerabilities you might not see. Let's look at how redundancy works in critical real-world systems. In spacecraft, engineers use triple modular redundancy with a voting mechanism to make mission-critical decisions. If one system fails, the other two still function. In hospitals, oxygen supply systems have multiple independent tanks with separate feed lines to ensure patient safety, even if one supply fails. In financial networks, banks use multiple internet service providers and redundant routing paths to ensure that transactions can continue flowing even if one network path becomes unavailable. These examples show why redundancy is so important in systems where failure is not an option.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.